Okay, very good. So I'll start. So first of all, thank you for the invitation. I'm sorry I could not make it for the event. So my talk is going to be around some work we've been doing the last 2 to 3 years here in Abu Dhabi called TelecomGPT, next generation AI for telecom network. I'm professor at Khalifa University and also director of the 6G Center within the university. And previously, I was working also at the Technology Innovation Institute, where I was a chief researcher in establishing what we call the AI unit. I'm still scientific AI advisor there and working, of course, on one of the main drivers of the UAE in terms of GPT, which is called Falcon. So a lot of the work that I'll be mentioning during my talk are in a series of papers that are available on arXiv related to the use of what we call LLMs or large language models, which I'll explain quite rapidly, related to the application in one of the verticals, which is of interest for us here within the realm of this 6G conference, which is the telecom domain. And so, of course, you can look at all these papers in more detail if you want to get all the information we're talking about. I don't think I need to go towards what is the definition of 6G. I think today we're having several people going in different directions, but we could summarize basically the series of generation within this 2G, which is mobile for voice, 3G mobile for data, 4G mobile for internet, 5G mobile for things. And today what we're trying to do basically is the fact that we are having some ubiquitous intelligence to be defined by the way what we mean by intelligence at each point of the network. Questions arise on how basically we can connect these intelligence. And just to give you two examples on why this is changing a lot of the realm of how the infrastructure is being built, let me give you one example. If you want to send a file from one point to another point of the network, and if you have a model at one point A and one point B, then basically it turns out that you don't really need to send the data to reconstruct the data. What you need to send is what we call instruction. So typically, in a more precise manner, what you would need to do if you have an image, you would do what we call an image to text on one side of the network. And on the other side of the network, you will send what we call the prompt, which is what we call the instruction. And on the other side, what you'll do is basically what we call text to image. And then you can reconstruct the image. Of course, basically, the big question here arises is that in general, if you do that kind of scheme to do basically communication in which basically with large language model, I've been showing you that there are super compressors, which is much better than what like standards like JPEG. Well, basically what happens is that you don't have a perfect reconstruction on the other side. And why we don't have a perfect reconstruction? Because at the end, what you're trying to do is what we call a rate distortion, trying to reconstruct perfectly the image. However, what I realize and when we communicate is that you don't need to have a perfect reconstruction as long as the message is the same. What I mean by that, if I ask you a question right now, you'll give me an answer. If I ask you the same question in 2 hours, you'll give me basically the same answer, but not the same sentence. But having the same answer is quite the same. And if you had the opportunity to use tools like ChatGPT, you realize that if you do a prompt, you'll get basically an answer. If you do basically a prompt in a couple of days, you will get basically the same answer, but not the same text. And the way we communicate is roughly the same way. So that gives you a bit of example that we're not trying to build a network in which basically data is being moved from one point to another point, but where instructions are being moved in one point to another point because you're able to reconstruct basically those things. Now, if you decide to go within that realm, one question that arises is if the 5G infrastructure that we have today is sufficiently reliable and good to do what we're doing. Well, one of the first things we realize is that if you want to go into this realm of being what we call doing image generation, for the example I give you, then you need to build up something of low latency mobile edge generation, not mobile edge computing, but mobile edge generation. Because as you can see, if you want to reconstruct that image, well, it has to go fast. And so basically the number of tokens per second that you need to generate is quite rapid. And so you need to build basically an end-to-end latency system which is compatible with the things I've been talking about. The second thing, of course, which also is quite important, is that we realize that these intelligence or on what they're based, like large language models, are like operating systems. And one of the questions, of course, that arises for people who are building the next generation network is, do we still need the same kind of approaches that we're building for example, applications? Why do you need an app today? on a phone. You don't really need an app. And by the way, in the last Mobile World Congress, there have been already some announcements of what we call app-free phones. Because at the end, what you're going to do is just ask basically your phone, I need a car below my house in 2 minutes. And then you'll have an agent which will go in a market, negotiate, and have your car. Today, when you want to have a car, you go on your phone, you browse on all the applications that you have downloaded. It takes you a bit of time, and then you select an application and you go. And so the notion of apps will also disappear in the next years. And the question is how you're going to build an infrastructure without apps, and in which basically these agents are going to be negotiating and finding a solution to your request. So these two examples show you already that we're having a shift today when you're starting having basically intelligence. Today, it's at the LLM level. It can change in a couple of years, and how we're going to do these things. Now, why are we at this conference? We're at this conference, what we call the 6G conference, because two things happened quite importantly last year in 2023. The first thing which happened last year was what we call the generative AI race. And I think you've been all quite familiar with the number of models which have been released starting the end of 2022, with, of course, ChatGPT and the release of models. And what's quite interesting is we've been seeing, and you can see this graph here, a big number of what we call closed source models, but also in our community, open source model, which are catching up. There's still a gap. I can explain why I think there's still going to be a gap related to closed source versus open source, but we're seeing a big progress basically of these large language model with extremely high capability. We'll talk about them and this high capabilities, how, of course, how we can use them in the telecom domain. As far as we're concerned here in the UAE, we've been building a series of model called the Falcon series. These Falcon series, if you're interested about them, they're open source model. We have a range going from 7B, 40B, and 180B. There's also one which is going to be released next week related to what we call a 10B. And they've been trained basically on a huge corpus of data, roughly 3.5 trillion tokens, and running, of course, on a lot of GPU. There's open source, meaning that, of course, you can use them and you can download them and you can already basically, of course, play with them and also fine-tune them to your own interest. There's also, for your information, a lot of strong engagement that we're seeing also related to Falcon as far as of today, with different companies already basically starting to use it because, of course, of its open source flavor and a lot of downloads. By the way, the Falcon series, and especially the Falcon 140B and the Falcon 180B, when they were released in March 2023 and basically in September 2023, they were ranked #1 on the leaderboard of Hugging Face. Now, if you've never heard about LLM, I'll do 3 slides to explain that because I think it's quite important, but I'm quite sure you heard about these things. What we're talking is about large language model, and it's a type of machine learning model that uses what we call model language as input and output. And they're trained on a vast amount of text data that can perform a variety of tasks. Differently, of course, from classical, what we call autoencoder, for which basically you train classical ML techniques for a single utility function, meaning you have a metric that you want to optimize. These large language models, of course, are able to adapt to a variety of tasks. And this is quite interesting because typically if you train a model to be good in addition and train a model to be good in division, it turns out also to be good in multiplication. Whereas in the classical realm of machine learning techniques like autoencoder, when you do some training specifically, for example, for a Rayleigh fading channel, then when you change basically the type of environment to rice, then it doesn't work perfectly as it should be. Now, why did these LLM basically become so important, and especially based on this GPT architecture? Well, before 2017, and 2017 was a key date in what we're talking, a lot of people who were doing basically what we call natural language processing were using classical statistical techniques, using classical architectures such as RNN, LSTM. This kind of architecture had some caveats. The first one is that they're not parallelizable. So if you have a lot of data, it takes you a lot of time to learn. Second is that they cannot learn long dependencies. And I think you're quite familiar with the classical ChatGPT. You're putting a long text and you're not putting a short text. In 2017, an important paper done by guys from Google, Google Research and University of Toronto, published a paper called Attention is All You Need. And in that paper, basically, they solved the 2 caveats that we talked about related to the classical NLP. They came up with an architecture called the transformer architecture, which is at the heart of what we call GPT, generative pre-trained transformer, which solve the two caveats, which is one, that they can learn long dependencies, and the second is that they are parallelizable. Now, what does modeling a language really mean? And what's the magic behind? Well, in general, what you want to do is the following. You have basically a text and you want to predict what we call is the next word or the next sentence, basically, or the next image. So here in the example that I'm giving you, you have the capital of the United Arab Emirates is Abu, and you need to find what's the next word. So you need to find what is the property of X, knowing that the capital of the United Arab Emirates is Abu. What is the property that X is equal, for example, to Nanjing, knowing that the capital of the United Arab Emirates is Abu? What is the capital of X being equal to Paris, knowing that the capital of the United Arab is Abu? And so what you're going to do is you're going to learn basically and model basically this, what we call conditional property distribution. So when you want to learn a conditional property distribution, what you do is that you're going to be able to what we call project it in a basis. So you're going to be approximating that thing because you cannot learn it in general. It's something very different. So one thing that could come up in your mind if you are doing a bit of mathematics is to say, I'm going to project it in a basis, which is a polynomial. I will say P of X is equal to A0 plus A1X plus A2X squared until AN to the power of Xn. And your goal then is to learn what we call the weights of your polynomial. And for doing that, you're going to minimize basically an error. Take all the text and the corpus that you have and basically be able to learn all the weights. And basically based on that, you will learn basically the projection of that conditional property distribution on a basis of a polynomial. And then any kind of the sentence that you have, you can predict the next word. So that seems quite easy to do. However, if you decide to do an implementation of what we're saying, it will become more complicated to do. It turns out that if you want to find the right basis on which you're going to project that conditional property distribution, it's not going to be an RNN, it's not going to be an MLP. It turns out that the transformer turned out to be a very good, what we call basis to do that, on which you're going to learn. And we have the routine in terms of training with gradient descents to do. The second thing also why these techniques related to what we call transformers and GPT architecture became famous is that it's a self-supervised problem. So you're not going to do the classical thing of labeling all the data on your own, which turns out to be extremely complicated. You'll have a routine basically that will enable you to do that. So that's very important. Another thing also, which is very important to tell you, is also that these things, when you start building them, it costs you a lot of money. And so this is why also not all the classical players that you've been seeing are basically leading this domain. You could ask yourself why it's not the top universities in China, which are basically building those top LLMs. Why it's not Stanford, why it's not Berkeley, why it's not MIT, and in general, it's more companies. Well, the main reason is that building a foundational model costs you a lot of money. This is a report from the BCG, Boston Consulting Group, and gives you a bit of a hint of the amounts we're talking about. If you want to develop basically a cutting-edge foundational model, we're talking about something like $50 million to $90 million. Numbers around GPT-4 are running around $90 million to $120 million. So it's a lot of money basically in terms of the cost. Of course, a big part of the cost is what we call the GPU. But then you have, of course, the training runs and basically also the people and R&D cost. Then you can do what we call enhancing existing foundational model. So what it means you take something which exists already, and then basically you feed it with complex company property data. But still there, you're around an amount of $1 to $10 million. And the last one that you could do is what we call the fine-tuning, which is what universities are doing. And also a lot of people who are doing TelecomGPT, for example, in which they take basically a classical foundational model with very good capability, and then they fine-tune it with telecom data. And this is where basically in general, academia has a role to play because we're talking about 10K to 100K. 10K to 100K, by the way, for academia is still a big amount for information. But that's only one part of the story. The second part of the story that is incurring a lot of issues for us within also the domain of the people who are building the infrastructure related to these LLM is, of course, the inference cost. Meaning every time you prompt a machine and we made a request, then it costs you energy and it costs you money. Typically for GPT-4, we're talking about 6 cents for 750 words. And depending on the speed on which you want to get those results, basically it can cost you more. And so this is also a big burden because basically operating those LLMs and serving them is not something easy. So even if you decide within the telecom realm to deploy basically this large language model, and you are the one hosting these LLMs, you need to take into account that it will cost you a lot of energy and will cost you a lot of money to do that. By the way, there's a very nice paper that I strongly encourage you to read called Choose Your Weapon, Survival Strategies for Depressed AI Academics. It's available in archive, and the paper tells exactly the crisis that basically the world today in academia is living, and for which I think industry should support now these guys to help them, because as you all know, the brightest guys I've ever seen today in science are in general in academia, because they have the freedom to do research. However, today they don't have any more the resources to do their work as they used to do. And if you read the abstract of this paper, it tells you a lot on the crisis today. What it says, well, are you an AI researcher as an academic institution? Are you anxious you are not coping with the current pace of AI advancements? Do you feel you have no or very limited access to the computational human resources required for an AI research breakthrough? You're not alone. We feel the same way. A growing number of AI academics can no longer find the means and resources to compete at a global scale. This is somewhat a recent phenomenon, but an accelerating one, with private actors investing enormous computing resources into cutting-edge AI research. Here we discuss what you can do to stay competitive while remaining an academic. And the paper says at the end, well, what you should do is mostly like focus on theoretical research and just look at proving theorems. I think academia has a bigger role to do that, and in which basically industry, and especially the guys working in 6G, should support those academics to start working on our interesting problems so they can move forward. And by the way, this crisis was so important here in the UAE that we decided basically last February to kickstart what we call a Falcon Foundation. So in our model that we built called the Falcon series that I've been talking about, we decided basically to give and build a foundation. And that foundation, what it does, it supports basically ambassadors in academia with compute as long as they work on Falcon. And we think it's very important because at the same time, we're supporting academia. And second, we're also creating a strong ecosystem, basically of users and adopting what we call the Falcon series. That was for the first part of 2023. The second thing which happened in 2023, and I'm going to talk about this convergence around TelecomGPT, is what we call the 6G kickoff race. And I think here I can go faster because I think you're all familiar with that topic. The first thing, of course, in June 2023 was the fact that ITUR WP 5D agreed on the IMT 2030 framework. And that was quite important because I think we're quite familiar with the fact that we were all fearful before 2023 of a fragmentation of 6G around the world with basically different standards happening. So that was a key date. And the second key date was also what happened here in Dubai, where we had more than 150 delegations with basically 1,500 delegates coming from all these countries discussing basically the spectrum related to the pre-6G allocation. And so that was a very important kickstart. And also basically where also the what we call the next generation connectivity metrics were roughly defined. I think within the 6G conference, I don't need to insist on that. You have all the details telling you how we're transiting from a classical triangle to basically something more of an hexagonal. And what's interesting is that, of course, we've been also mapping all these basically different, I would say, KPIs to technologies. As of today, within, I would say, the 6G, I would say, realm of researchers, you can cut the thing in three categories. One around broadband connectivity, another one around sensing and control, and the last one around intelligence, on which I'll be talking about right now. And basically what we have a couple of candidate technologies today, which could fulfill some of those requirements. I think we're still at the starting stage. There's still some work to do. But what we're seeing is in terms of broadband connectivity, and I'm going to give you the list, what are the possible technologies? And these goes from holographic MIMO to terabit coding to OEM to cell-free massive architecture to, of course, large intelligent surfaces, millimeter wave, what we call satellite, beyond OFDM waveforms, ultra-massive access, and time reversal. On the sensing and control part, what we're saying is joint sensing and communication waveform, terahertz communication, wireless imaging, extreme URLC, age of information, and beyond sampling. On the intelligence side, and this is where I'm going to spend more time today on, we're seeing also, of course, a couple of candidates trying to push something like distributed GPT, edge learning, semantic source code, semantic channel codes, multi-agent generative AI, and AI transceiver. Now, what are we talking now about this convergence that I talked, which is on the third pillar? Well, on the TelecomGPT pillar that I want to introduce you today, we're seeing three things happening. The first one is basically a big push related to the fact that we should now build large language model that can run on small devices, which is basically being able to do these basically LLM on device. And you have here two approaches. One, either what I call a post-processing approach, taking a big model and trying basically to shrink it by quantization distillation, or trying to build a large language model taking into account the hardware constraint, like basically binary neural network. The second thing also, which is being more important for us, is how we can construct now more and more large language model which are adapted to our setting. Setting being multimodality. Multimodality because we have cameras, we have RF signals, we have sound, we may have smell. How we incorporate all that knowledge basically in terms of building a large multimodal language based on all the telecom data that we have, so that basically we can improve the communication. And the last one where I think there's a lot of potential is, of course, building the platform that connects these agents together at the speed which is required. And the speed which is required, again, is this end-to-end latency on which basically it's not just about the communication, but the computing, or what we call the mobile edge generation at which this happened, and how the system can self-organize by itself. And these are the three pillars that I'm talking about in the TelecomGPT realm. You have to know that because of that, we have decided, and because of the hard task that this requires, we have decided basically in a more academic flavor, to be honest, to build up what we call an ETI, an Emerging Technology Initiative. Basically, I'm chairing it, by the way, in which we have different players, and especially a lot of players from China, going from, of course, China Mobile to Huawei to universities, which are implicated, and in which we are basically trying to promote, trying to organize, trying to create an ecosystem of basically researchers which are contributing within the realm of what we call here the large generative AI models in telecom. My previous basically colleague had spoken about now a couple of use cases and application, and I'm going to go rapidly because I don't have much time left on what we're seeing today. I think my previous colleague already mentioned the fact that we're seeing two things happening. One, the usage of what we call multimodal language model to improve the telecom domain. And the second is how we can get back, and especially operators, a piece of the cake by building the infrastructure to connect these distributed GPT in a very sound manner. And the fact that we want to build today in TelecomGPT based on open source Telecom Falcon, that's what we're doing here in the UAE, goes on developing basically these four pillars that I mentioned about. Fine-tuning Falcon on telecom knowledge, develop Falcon-powered telecom AI agent, expand Falcon on multimodality RF generation, and develop Falcon-powered multi-agent network for information. I'm going to give you two examples that we've been working on. The first one, of course, is fine-tuning Falcon with standard specification, where we took a lot of 3GPP documents and other documents, and so we could do the prompting in a very good manner to get nearly all the answers. So basically today, if you want to do, for example, a TDoc, you could write basically just some kind of rough, let's say, prompt, and basically based on that, you can generate the TDoc. And here I'm going to give you an example that we did, where we did some what we call instruct tuning on 3GPP task completion. For example, we give an instruction here, which is generate the procedure of the following RSC configuration. We put radio bearer configuration, and as you can see, you get all this as an output, which is extremely important and helpful for our guys and engineers who are working in the telecom domain. And we have a lot of examples like this, where here you have on the right side, generate the messages for executing the following RSC configuration, radio bearer configuration, and as you can see here, it provides you a lot of details. So by doing a lot of training on telecom data, of course, you could do a lot of 3GPP task completion and other things which are extremely useful for our domain. The second thing, as an example also that we've been working on, is how to build multimodal signals or multimodal models to do what we call 3D imaging. Instead of doing text to image, how we can do RF to image. And basically, based on a lot of image related to different RF configuration, how basically we can do that kind of things. And this is very important for everything which is related to what we call 3D imaging. And for that, we have here a couple of examples we worked on where the idea was to build an RF visual language model that generalized different wireless sensing tasks with prompts. Here you have an environmental image, you have a channel measurements, you have an image encoder, you have an RF encoder, you do what we call an image embedding, RF embedding, image decoder and RF decoder. And the idea is, of course, to be able to reconstruct based on RF to image and image to RF, basically, so you can construct the most probable image that you want to have. And here you can see some of the examples we've been working on this, what we call multitask wireless sensing, and looking at the pairs called signal to image. When we talk about signal, of course, is the signal signature or radio frequency signature that you have related to environment. For doing that, of course, we use a lot of what we call synthetic data, in the sense that we launch some ray tracing with our simulator to get a lot of different environment related to the RF so that we have sufficient data for doing that. We're not an operator. We don't have basically what we call 3D maps of a city and doing those things. So in general, we use RF basically simulator to build this kind of approach that we're doing. But this is also something that gives you on the kind of things that is quite promising when you start building what we call these multimodal models, on which you take all that information that is there to basically output for the image and sensing things. And the third one, of course, that I think is also important is what we call the telecom AI agent. And being able basically to build up a system or an architecture where you have perception, action, planning, and memory, and on which basically LLMs are at different points of the network, meaning on the mobile phone, on the base station, and you're enabling them to give them a certain, I would say, objective, and let them basically run the system so that they can interact and solve your problem. Because these LLMs, again, are what we call distributed optimizers, and this is something that we've been working on this example typically, where the goal was to minimize the energy consumption while having a target fixed rate. And so here you have an LLM on the base station, you have an LLM on the phone, By the way, this is a simulated environment, so it's not like really implemented. And the idea is that we ask a base station where we give a prompt, consider a downlink channel with one base station and 4 users. The noise level is the same for all users and equals a certain number of watt. The bandwidth is 15 kilohertz. The channel gain vector we give them. The initial transmission power vector we give them. Base station aims at reducing the total transmission power by 0.85 watt at least. And then we let the system run by iteration to solve that problem so that we get basically at the end a certain, basically with the prompt decision at the base station on the transmitted power. And so today, there's a lot of examples today of people using these large language model as what we call optimizers to solve those kinds of problems. You can see a lot of papers also going within that direction.